Good morning, everyone. This is Jim Chastain with EasyPower. Welcome to our Tuesday Refresher webinar series. Appreciate your joining us today. And the topic is basically in response to several questions that we get over time and during trainings. And it's something that comes up now and again as people are doing studies. So we thought we'd kind of cover a whole list of topics, and frankly, none of the discussion will be that in depth on any one. So we're trying to basically cover the application of the tools to these particular items. So we will be talking about the damage curves for transformers, how to do, or at least the recommendations for coordinating with fuses, comparing low voltage power circuit breakers and molded case circuit breakers, and attempting series coordination with those. Talk a little bit about sequence of events, and then the coordination time intervals on the TCCs. So again, thank you for joining us. And as we're wont to do, we'd like to start off with a poll question. So if you would please help us with the response. And obviously there's no obligation, but the first question has to do with which types of protective devices give you the most problems. And again, these are pretty wide open topics, and we get questions coming from all directions. So hopefully we'll be able to shed some light on it, although I'm willing to bet we're not going to answer anybody thoroughly as far as satisfying your particular needs, but we're going to give it a try. So it looks like we've got a quorum here on the poll question. Here's how folks have weighed in on this, and it looks like at least our agenda is going to be helpful. And then the second question is, which task provides more problems for you? And that basically is comparing coordination versus mitigation. And to some extent, as we're doing coordination, we're really kind of ignoring mitigation. So there's a cross purposes here that poses a problem for anyone trying to do a study comprehensively. Thank you for attending today. It looks like we've got a quorum here on this poll question, and it looks like we're leaning a little bit more towards mitigation. And again, I appreciate your participation and joining us today. So let's jump into the discussion. So on the topic of transformer damage curves, there are kind of two guiding lights, if you will, in the industry, and these are standards that are produced by I2t and ANSI. And ANSI C57109 is specifically damage characteristics for oil-filled transformers, and ANSI C57.12.59 gets into the details of damage constraints on dry transformers. The reason these are important is that as we're getting into the use of the tools, based upon what we've entered in the description of the transformer itself, will determine the standard that EasyPower uses to analyze our circuits. What we will produce in our TCC curves for the transformers are going to look something like this. The upper part of the curve, and this is a typical shape, if you will, of a transformer damage curve. The upper portion, which is the lower current, is where the thermal damage is considered the most probable failure mechanism. And at the higher current, these are subject to the magnetic effects of the higher current, which can cause mechanical damage to the structures of the windings. This hook in the, or the crook in the display is actually what's described as frequent faults, and they reduce the limitations for circuits or systems that expect to see more frequent faults than overwhelming damage curves. So the question comes up, well, what is a frequent fault, and how does that fit into the discussion? Well, if we go back to these standards, we can see that they're, at least for an oil field, they're described by these limitations, and they describe different categories based upon the size of the transformer and the category that's in. And this is where the basic shape of the curve based upon the category and the impedance of the transformer itself. And so we're going to jump into that when we get into the discussions about frequent faults. Now, as far as the two sets of curves, there comes into play a situation where there's a different methodology as far as the display of the currents that we're monitoring with the CTs, and it has to do with the difference between the windings on each side, in particular a delta Y constructed transformer. And so what we're talking about as far as a per unit is the current that we're monitoring in the secondary winding and how it represents what's being produced or driven by the primary side. And so what we're talking about, it really only applies to through faults because we can't detect on the secondary side any internal damage, and there's no way we can protect it by monitoring on the secondary side because the damage has already occurred. But because we're looking at one side or the other, we need to compensate for this difference in the displays. And so what causes this, or the result of this, is when we're monitoring the per phase, have CTs on each of the phases in the secondary, a 1 per unit value has a correlation to the current in the primary, but it's not a 1-for-1 because let's say on this particular phase in a delta system, it's the sum of these two currents, whereas what we're monitoring in this phase is the phase in that particular winding. But when there's a normal full load, that relationship stays constant and is proportional, as I say, to a ratio that we can predict. On the other hand, when we have a line to ground fault on the secondary, then we don't see that same correlation to the phase current on the primary side. And so we have to do, and what we're basically saying is that this current is going to be the sum of the two phases that correspond to that particular phase in the primary side. So again, we're talking only about through faults, and we're only talking about single line to ground that need to be derated or compensated. And this is what it looks like in EasyPower. Let's jump into the tools and talk about this. All right, so here's a transformer that's a delta Y, and if we go to coordination and plot the curves, we can see, just as that previous slide showed, we have two different curves. We have this crook in the lower portion of the higher current, and this is where the frequent fault curve is defined. And if we uncheck that, we remove the limitation or the need to be concerned about frequent faults. So again, if we don't have frequent faults, then we have a little bit more headroom, if you will, as far as the protection of the transformer. If we're subject to the frequent faults as defined by that ANSI standard, then we need to basically make sure we don't exceed these particular limits. Now, the the unbalanced derating is a function of this solid line, and it's only again for through faults on a single line to ground. So we can basically ignore it when we do a three-phase fault. On the other hand, when we're doing a single line to ground fault and ground coordination, we need to have that in there. And then thirdly, the 100% withstand curve is the dotted line at the top, and that's the one that primarily we're focused on as far as coordinating downstream protection. One other thing to point out is the inrush current, which is some function based upon the full load current, and it's defined by these parameters in our setup. And again, it's a consideration when we're talking about primary protection, and consequently on the secondary side, this really has no meaning as far as our ability to protect the curve. Okay, so I wanted to look at a couple other. So this is a typical delta Y with the Y grounded at 1500 kVA. Here's a delta delta, and just showing this to show the difference in the curves. Again, we have the D rating is 87% rather than the 58%, and it's a function of, again, this unbalanced checkbox. And then thirdly, it's interesting to note that if we're looking at a smaller transformer, 500 kVA or less, and in this case I have a delta Y with no ground, what we see is there's only the maximum 100% curve, and that's due to a couple things. We request frequent faults, but because this is 500 kV or less, there's no description or no limitation or no relaxation for frequent faults. And then because this is a delta Y, the 100% curve represents the same plot, and again because of the smaller size of the transformer. Okay, so that's what we're looking at as far as trying to do coordination involving transformers. Let's jump into our next topic. And this has to do with fuse coordination. So the bottom line is fuses aren't adjustable, and it's difficult to expect coordination between different manufacturers, primarily because the test and the specs for each particular one may be different across the manufacturer's boundaries. So the rule of thumb as far as coordination is you need to stay with the same manufacturer and the same model, and then as you coordinate the next upstream, fuse needs to be 2x the size of the one downstream. So to illustrate that, and again, this is rule of thumb. Outside of these recommendations, the chances are pretty slim unless you're right on top of the damage curves, the TCC constraints. There's a pretty slim chance that you will get coordination. Let me go back to my one-line diagram, and we will see if I can't illustrate this. So what I have set up here are two curves, two fuses on the primary side of this 1500 kVA transformer. And as we look at it, I'm showing FS2, which is this one right here, FS3, which is right here, and I've basically said, okay, well, what happens if, so this is FS3, which is on the secondary side, so it frankly doesn't fall into the guarantee because it's not even the same manufacturer as the other two fuses. So the question is, if I wanted to coordinate with other parts of the circuit, is there another fuse I could put in series with these that would allow me to do the coordination? One of the ways to look at it is say, well, I want to look at a new curve and an AC high voltage fuse. And I know my manufacturer in this case is AB Chance. I know I'm using a standard fuse type C, and it's a Model T. And because I want to be 2x, let's look at a 80 amp plot, and we can see now that except at very high currents, we got a fairly good coordination between these three fuses. Now, whether or not this fuse does what we want it to do is another question, but the fact is, if I have a load that my expected fault curves are going to be in the lower boundary or less than the upper end of this plot, I have a good chance of being able to coordinate at least for this particular area. So there's a couple things going on. One, we're verifying that we have coordination between the fuses, and two, we're saying, well, what if I had another device. In this case, I just picked out a fuse, but that gives us some direction to take the discussion. Clearly, if we wanted to pick up another manufacturer and see that that's something we might want to consider, but there's no guarantee at that point. Okay, so the bottom line is, as far as fuses, try to stay with the same manufacturer, and if you're trying to coordinate, basically do 2x what the downstream value is, and you have a pretty good chance of being able to coordinate with the fuses. Now, the topics of molded case circuit breakers versus low power circuit breakers. It's pretty much understood that because instantaneous trip is included as part of the standard design of a molded case circuit breaker, it's very difficult to coordinate because you have overlapping instantaneous trips. Now, normally, molded case circuit breakers are used in switchboards, which are actually governed, if you will, or stipulated by a different standard than switch gear, which is used for low voltage power circuit breaker characterization. Because molded case circuit breakers aren't tested at maximum current, at rated current, they're only basically guaranteed for 80% of the rated current as compared to low voltage power circuit breakers, which by virtue of this regulation have to be tested at 100% current and be capable of carrying the fault current for two periods of 30 cycles each. So consequently, although it may be how we designate our particular feature set on the low voltage power circuit breaker, it's easier to coordinate because of the adjustability and the if you will, ability to disregard or turn off the instantaneous trip setting. Now, there are some molded case circuit breakers that have the ability to adjust that instantaneous trip, and you'll see as we get into the curves that it's being fudged a little bit just because they end up using a solid state trip unit similar to a low voltage power circuit breaker. So let's jump out of this particular plot and open up our so here we have basically two radial legs, one that we've used primarily molded case circuit breakers, and one where we've used low voltage power circuit breakers. And looking at the molded case circuit breaker side, we can see that there's always going to be, because of the instantaneous setting in both of these, even though they're adjustable, there's a potential for miscoordination. And in this case, at least at the higher end of things, you could have a chance for at least not being sure which is going to trip first. Now, because of these particular trip units, we can turn off this trip setting on instantaneous. We just turn it off. And at that point, we have a better chance for coordination at the higher currents. Now, again, that's because there is a square D micrologic sensor trip unit, and we have the versatility of being able to disable that instantaneous trip. If we're using just straight off the shelf, non-adjustable molded case circuit breakers, that's much more difficult. Now, let's talk about low voltage power circuit breakers first, and then we'll go into series coordination. Whereas if we took the same type of a system and plot the TCC curves for the low voltage power circuit breakers, this adjustability makes it relatively easy because we don't have the instantaneous set on either one. It makes it relatively easy to be able to coordinate and ensure coordination even at the different current levels in my circuit. Okay, so that seems kind of obvious. The thing that's less obvious is the discussion about series coordination. So it turns out there are some constraints that allow us by test to expect the ability for particular devices to be able to coordinate. And this is due to constraints in testing that manufacturers have published. And in the case of the EasyPower device library, this coordination or this series coordination capability is part of the device library indication, but we can see it on the TCC. So let me talk about that one a little bit. And it shows up, and we'll look at the device library shortly. It shows up in the TCC when we plot the curves. So right now, by selection, I've picked out two square D parts that, according to the manufacturer, have the ability to coordinate. And so as we look at the plot, because this information is in the device library, there's a note in EasyPower that says, per the manufacturer, BL5 and BL7 are coordinated to 35,000 amps when BL5 is off or max. So if we come in here and look at BL5 and turn off the instantaneous pickup, again, we can see how that allows. And so that gives us the ability now to be coordinated up to that particular point. So if we look at our current, now this this is showing that we're just over that limit as far as what the guarantee is, but the curve seems pretty straightforward as far as ensuring that we're series coordinated at that particular level. Now, how that looks in the device library appears like this. So if we go in and look at our device library, I want to look at square D, I think it's R. So multi-case circuit breakers, AC. Let's look at square D. I think it's the R frame that I'm using. So if I had selected an RG as far as my upstream device, then the device library will show me for that upstream and amp setting that these breaker selection styles and sizes on plugs will coordinate up to a certain level. So it starts off with 240 volts. And if we slide down here to 480, we can see that for 125 amps, 150 amps, 400 amp trip settings, we will coordinate with these downstream breakers given the selection, the recommendation from the manufacturer. And so it's this correlation between the part numbers, sizing, and the selection of part downstream that will produce that tick mark and label on the TCC plot. Now, with that said, let's kind of go back and talk about that curve. As we look at, I want to talk a little bit about TCC clipping. If we look at our short circuit setup for any particular breaker, in this case, we picked this main breaker BL5. As I'm setting up my breaker, I have the ability to use clipping so that we don't display current beyond the point that the maximum for this particular device. If I set this to none, I can see that there's no limit, an upper limit to the display, even though the breaker's not exposed to anything higher than that particular limit. We can use momentary current if we're looking for what the interrupting current would be. And so this will clip at any particular set point we want. Most often I would use momentary current because that's the highest current along the way. But if we want to see the characteristics of the part, that we just turn this part off. Now, likewise, there's tick marks that are based upon those interrupting 30 cycle and momentary current. And as we fault a bus, that will produce these tick marks, which are down here at the bottom. And so it's useful to find the maximum current through this breaker will be displayed right here on this tick mark. And that's the case for any bus that we fault. Okay, so that was series coordination that was guaranteed by test. The devices listed in the way we can look them up in the device library, and how the tick mark shows up on the TCC when we have a guarantee from the manufacturer due to that testing, and then how to take advantage of the TCC clipping for purposes of either cleaning up or distracting plots, or verifying that we're coordinating in the right area of the curve. Now, what I consider probably one of the most useful features of the power protector module, which is what's used for coordination, is the often unsung utility called sequence of events. It's actually built into the tool, and frankly, I use it anytime I'm trying to look at where the origin of a particular fault may lie, especially when we're talking about instant energy. And so let's kind of jump into this and talk about it. I'm going to go back and let's close this guy out. And it's most useful, in fact, I found it extremely useful in the more complicated systems that can have multiple sources, because the fact that it's going to show me from a single bus fault, it's going to show me all the chronological tripping for any device between the fault and the upstream energy source. And so when I have cross ties or multiple sources like solar or turbines that may be lower current, that this is one way to kind of verify what's going on between the different power sources. All right, so I'm in coordination. I'm going to pick a downstream bus. I'm looking at current, and I'm going to fault that bus. If I have, and I'm going to look at short circuit options. If I have under short circuit options on my one-line display that I'm showing all remote voltage and current for a single bus fault, I will get this type of a display then when I faulted a single bus. And that is during the first half cycle of current. During the first half cycle of my fault, I will have 130 amps contributed to the fault from this motor control center, 130 amps contributed here, 120 here. So that total of 370 amps is contributed up through the transformers and back down, and it's part of the 18850 that's coming from upstream. And just kind of to make note, the utility is supplying 640 amps, and this other contribution current is a little over 10 amps listed at the 13K level. So it all contributes into my fault. Now you say, well, why do I care about this? When we start to do coordination, we need to know, or at least to set up the timing devices, we need to know what's going on with these counter-opposing currents. When I'm in this condition, that is a single bus fault looking at current, the tool makes available to me the sequence of events icon on the second row up here at the top. As I click on that, now rather than current, the tool shows me the chronological tripping order of every upstream device between the fault and the energy source. So if this bus faults, this breaker will trip in 190 milliseconds, this breaker will trip in 35 seconds, this fuse will trip in 32 seconds, and this relay will trip in 300 milliseconds. Now what I do about that is basically go into coordination and deal with it But the point is, the more complicated my system, the more valuable this particular tool is. If I have cross connects and multiple energy sources, I can have contributions that's limiting my or causing my calculations for instant energy to be very high, because it's causing a longer trip setting on the last device that's being tripped or being monitored. So this is one way to make sure you know what's contributing to your instant energy. So anyway, if you want to see a report with this information, it's called the Sequence of Events Report. It's under PDC Options. Under General, right-hand column, last line, Sequence of Events. We come back and fault this particular bus again. And then that report shows up under my list of windows as a Sequence of Events report. And as I say, this can be very complicated if we're talking about a complicated system, but it sure saves a lot of time because I can spin my wheels trying to coordinate one leg of the system when the actual low energy source is off on another radio. It's happened before. All right. And then the last thing we want to talk about was coordination time intervals. So these are typical coordination time intervals between upstream devices and downstream devices. And generally, if you have electromechanical relay, you want to have at least 300 milliseconds coordination time interval between them. And so what we're talking about here is if we have electromechanical relay and in series with the digital relay, you want to have 250 milliseconds. If it's in series with a direct acting trip, 200 milliseconds, and with a fuse, 200 milliseconds. And so probably the one, and again, these are typical, and the guard band is left up to the engineering judgment. But the one that's probably most significant is the direct acting trip unit, which are the breakers and the solid state trip units. As long as we get daylight separation between the two device strip settings, then that's considered adequate. So I want to look at how this shows up in EasyPower. And so again, let's plot our, I'm going to go ahead and start with this large motor, plot the curves, and we can see because we knew the relay was tripping quicker or sooner than it should, we knew that it was going to be miscoordinated. And sure enough, here it is down below everything but the last inline breaker. So what I'm going to do is invoke Smart PDC. It's going to replot the curves for me. And now I want to see what my coordination time interval is between the different devices. I pick out one device, hold down Control or Shift, pick out the second one, and then I invoke the difference calculator. And this shows me the minimum time separation, it's a CTI, between each of the devices. Now, if I wanted to, and I want to indicate by right-clicking on the tripping device and inserting the arc fault current, I would be able to set my CTI measurement over that. If I select the 2, I can do the CTI between the breaker and the relay, and we see it's 102 milliseconds, and that's the minimum amount. And then if I want to do the relay to the fuse, I can do that there as well. Okay, so that's how you measure CTI, or the difference calculator, between the curves. Select the 2 curves and then invoke the difference calculator. All right, so that's kind of runs out of time. Let's see where we are on our agenda. I do want to bring up that we have regional training locations set for the first half of this year. Welcome you all back to attend future webinars. And if you or so inclined, check out the online training alternatives, which is the same information as contained in regional training. It's just available online. And then if you have questions or need help with the tools, please contact tech support at easypower.com. Thank you for attending. Sorry we didn't have time to get to any questions. I will be responding to any questions submitted via email. Thank you all for attending, and we'll talk to you later. So long.